Momentum. It can be defined as inertia in motion, moving mass. From a conceptual standpoint, it's a lot like even in sports, where you have a team has the momentum. They're on a roll. They're catching up if they're behind, or they're getting further ahead. Something's going for them. Now, mathematically, the equation for momentum is P equals mv. The most difficult part about momentum is probably the letter that we use, and for some reason we use the small case p, which is a leftover from some kind of Latin root word for momentum, but lowercase p here means momentum. M is mass. We want our mass measured in kilograms in these problems, so convert to kilograms if they're not in kilograms. V is going to be the velocity in meters per second, which means momentum will have units of kilograms meters per second. So those are the units for momentum, which is kind of strange, but kilograms meters per second, kilograms times meters per second will be the units. Momentum is a vector. It has magnitude and direction. I can ask you this: does a freight train have more momentum than a tennis ball? And the answer is, it depends. Typically it would. If they're going the same speed, definitely a freight train would. But the answer is depends on how fast each item is moving. How fast they are moving. Their velocities. For example, if the freight train's not moving at all, and the tennis ball is moving, the tennis ball has some momentum, the freight train has none, because you have to be moving to have momentum. Or if the freight train's moving and the tennis ball is moving at like almost light speed, it could have more momentum. It would need a lot of speed or velocity to have more momentum than a moving freight train, because a moving freight train would have so much more mass than a tennis ball. But momentum depends on mass and velocity. The law of conservation of momentum says with no external forces, the net momentum of a system does not change. Now, there are two types of collisions that we're going to be dealing with to apply the law of conservation of momentum, plus explosions. We'll talk about that in a minute. But in an elastic collision, it's a collision defined as a collision with no energy loss. These are very bouncy situations like super balls, trampolines, anything that's really, really bouncy is elastic. Inelastic is a collision where some energy is transferred to heat. Things that are not very bouncy. Dropping a big wad of clay onto the ground, it would just kind of basically stick there. However, in our macroscopic world, almost all collisions are at least somewhat inelastic. There's almost always some energy loss. For example, even with a super ball, when it bounces, we could say it's an elastic bounce, which we would. It tends towards elastic, but it's not perfectly elastic, because if a super ball had a perfectly elastic bounce, it would bounce to the same height at which you dropped it at. And we know that doesn't happen. When you drop a super ball, it might only come up like maybe in the best case 75, 80, 90% maybe of its initial height, but eventually, well, it never comes up to its initial height. So it's never perfectly elastic in its collision. In the microscopic world, when you have like gas particles in a container bouncing off each other, those could be pretty much nearly perfectly elastic, but we can't see that. However, in either case, momentum is always conserved. Whether you have an inelastic or elastic collision, momentum is always conserved. So let's take a look at some of the calculations here. First of all, just simply calculating momentum, applying the equation P equals mv. Say we have a bowling ball rolling at 18.2 meters per second. The momentum is going to be the mass of the ball, 6.3 kilograms. We're good with our mass, the units, kilograms, times 18.2 meters per second. And if you multiply those, you get P equals 115 kilograms meters per second. And that would be the magnitude of the momentum. We don't need to worry about direction yet. Let's say you have a fish swimming in a lake Once again, P equals mv. It's very simple. Just watch your units. The mass of the fish is good, 2.7 kilograms times the velocity in meters per second. That's 0.78. 0.78 meters per second. So the momentum of the fish is 2.1 kilograms meters per second. Once again, that's the magnitude. We don't need to worry about the direction. All right, a bullet. Once again, just plugging into P equals mv. Watch out for the mass here. The mass of the bullet, we want that in kilograms. Convert to kilograms, that's 0.023 kilograms times 315 meters per second. So the momentum of the bullet is 7.2 kilograms meters per second. So those are simple examples of how to calculate momentum. Just watch out for the units. You take the mass times the velocity. So here in example 1, we're going to apply the law of conservation of momentum to a collision, a bowling ball hitting a bowling pin. I've sketched this out. Sorry about the exactness of this diagram, but basically you have a bowling ball heading for a pin. It's going to hit the pin. It's going to cause the ball to slow down, but the question is, what is the final velocity of the ball? So we have before the collision, and all conservation of momentum problems work like this. You have it before the event and then after the event, and momentum is conserved. So here's what happens. I'm going to call this, for the bowling ball, P1 equals M1 V1, and for the bowling pin, we have P2 equals M2 V2. Now, we already calculated on the previous side of this page, or the previous page, that for the bowling ball, its momentum going in from problem number 1 was 115. You can look back at that. Kilograms meters per second. Well, P2 here for the bowling pin is 0 because it's not even moving. All right, so what we're interested in is the total momentum here. Well, the total momentum here in this system is just the addition of 115 plus 0, it's just 115 kilograms meters per second. So that's what's going to be conserved, that number. We need to have that much momentum after the collision. So now we're going to do this on the right-hand side here. We're going to call this P3 for the bowling ball after the collision equals M3 V3. And for the bowling pin, P4 equals M4 V4. Once again, P stands for momentum. Now I do know that after the collision, the bowling pin, P4, is its mass, which is given in a problem, to be 2.7 kilograms, times its final velocity here of 5.2. It's 5.2 meters per second. So the momentum of the bowling pin after it's struck is 41 kilograms meters per second to the right. Now, all the momentum here is to the right. Now, I do know that in this after part over here, that P3 plus P4 must equal 115. Now, where did I get that 115 from? Well, from the before the collision. This part way over here, I'm bringing it over. All right? So if I know that P4 is 41, so what I have here is P3 plus 41 equals 115. That tells me that P3 must equal 74. So P3, if I subtract here, P3 equals 74, and the units are kilograms meters per second. What I'm going to do with that is I'm going to come over here to this equation, circle it in blue. I know that P3 now is 74. So 74 equals the mass of the ball. The mass of the ball is still what it was in problem number 1. The mass of the ball was 6.3 kilograms times V3. This is what we're after here now in blue. So V3, the momentum of the velocity of the ball after it hits the pin is 11.7. You can round that off to 12. 11.7 meters per second. That's the speed of the ball after it hits the pin. It got slowed down. All right, example number 2, or actually number 4 or 5. Number 5. The big fish is going to eat the small fish. The big fish, we're going to call that P1 equals M1V1. We already calculated that from problem number 2. And in problem number 2, that came out to be P1 was 2.1 kilograms meters per second. Now the little fish is not moving, it's just kind of floating there. Maybe he doesn't see the big fish. So P2 equals 0. So P total, which is once again going to be conserved, is simply the 2.1 kilograms meters per second. That's what's conserved. All right, so the big fish is now happy after lunch. We're going to call this P3 equals M3V3. You can see by the big smile on his face that he's feeling pretty good with that little guy inside him. But this is what's conserved. This goes over here for P3 because now we only have one basically big object after lunch. The total momentum belongs to that one object, the big fish with the little fish combined. So it's 2.1 units of momentum equals mass 3. But now mass 3 is going to be the sum of the two masses because now they're together. And the big fish was 2.70 kilograms, or by itself it was. The little guy in kilograms is 0.15 kilograms. 150 grams is 0.15 kilograms. And now we have times V3, which is the combined velocity. Once again, if you add the 2.70 plus the 2, well, it's 2.1 equals 2.85 V3. We get V3, the velocity of the big fish with the little fish inside him, as 0.74 meters per second after lunch. That's our answer. Let me make that blue. There's the answer. The final example here for conservation of momentum, we have an explosion. Now these tend to be the easiest type to analyze because, once again, like any of the momentum problems, you always have a before and after. Before the event, before the explosion here, and then after the explosion. But in an explosion problem, what makes it easy is that before the event, let's call this P1 equals M1V1, the momentum is 0. Nothing's moving. So P1, which is P total, is 0. 0 kilograms meters per second. There's nothing moving. So that's what our momentum must be afterwards. That's what's conserved. The momentum before the collision or event, explosion here, is equal to the momentum afterwards. Now in this case, let me switch to black. I'm going to call this P2 for the gun equals M2V2. That's gun. And for the bullet, P3 equals M3V3. But we've already figured out the bullet from problem number 3 on the first page. The bullet, you can go back and look, the bullet had the mass of 23 grams, 0.023 kilograms, times its velocity of 315. That came out to be 7.2 kilograms meters per second of momentum. If you needed to do that over again, you could show the work for that, but that's what the momentum of the bullet is. We did that in problem number 3. Well, what this means is the gun, and if you want to use negatives, you can, which is P2, must have a momentum of negative 7.2 kilograms meters per second because the total, if you add these up, must be 0. The backward momentum of the gun must equal the forward momentum of the bullet. So that's what we're going to then plug in over here. All right, and you don't need a negative. You can put it in if you want. 7.2 equals mass of gun, which was the 2.6 kilograms, times V2. V2, the backward recoil velocity of the gun, comes out to be, I believe, 2.8 meters per second. 2.8 meters per second. Recoil velocity. Give that in blue. That's our recoil velocity of the gun.